My name is Sara Robinson. I'm a developer advocate on the Google Cloud team. If my audio cuts out at any moment, just interrupt and let me know, and I will try to fix it. You can find me on Twitter at @srobtweet, and I blog at sararobinson.dev. So what I'm going to be talking about today is first, I'm going to explain what design patterns are, talk a little bit about the book that Anna mentioned, then I'll define responsible AI, and then I'm going to spend the bulk of the time talking about 3 patterns for responsible AI with some live demos. So first of all, what do I mean when I'm talking about design patterns? So what design patterns are is they're best practices for solving common problems in software engineering. Could relate to any aspect of software engineering. The patterns that I'm going to talk about here are specifically related to machine learning and within that, the field of responsible AI. So what do I mean by design patterns? This is super exciting. So I wrote a book with 2 of my teammates, Lack, who is speaking later on today. You should definitely catch his presentation. And my teammate Mike. You can follow Lack and I on Twitter. If you want to pre-order the book, there's a link right here that'll take you to Amazon to pre-order. It should be released beginning of November. So I'm going to be covering the patterns that are mentioned in this book related to responsible AI. Lack is going to be talking about some of the patterns related to ML ops. So if you're interested in that, check out the schedule and tune into his talk. Just a quick preview. I know this is pretty small, so you may not be able to read it all. Just a teaser for the book. This is a diagram from the last chapter, the summary chapter in our book. And the book is written, organized by different phases of the machine learning workflow, from gathering your data to figuring out how to represent the machine learning problem you're solving, training and deploying models, and then finally responsible AI. So this is just a summary of all the different patterns that are covered in the book. So let's dive into responsible AI. I want to start out by defining what responsible AI is. Essentially, responsible AI is the practice of ensuring that machine learning models don't reinforce unfair bias. And responsible AI is an umbrella term that encompasses a bunch of different concepts. These are fairness, explainability, privacy, and security. And we don't cover all of these in the book. We just touch on a few of them. But just wanted to set the context for what responsible AI is. And then just a bit of background on why responsible AI is important and why you should care. So this is a recent industry report that was released that found that for companies, trusting AI systems was their biggest barrier to deploying machine learning models in production. And 90% of organizations have encountered issues related to ethics and AI. And 40% of companies just decide altogether not to use AI when they encounter these issues. I won't read all of this slide in detail, but these are just some of the issues related to ethics that companies have encountered when building machine learning. And at Google, we believe that responsible AI systems benefit everyone and ultimately lead to successful AI. So to summarize, these are the 4 different concepts that are related to responsible AI. I'm going to be touching mostly on fairness and explainability. And so in our book, we have 3 different patterns for responsible AI, and that's what I'm going to be covering here. So just a quick intro to each of these. Heuristic Benchmark is a pattern that's meant for when you're starting out developing a model. It's meant to provide a starting point for summarizing this model maybe to non-technical stakeholders, and just a starting point for a benchmark to evaluate your model relative to something. Explainable Predictions goes one step further, and once you have a trained model, this pattern provides some techniques for understanding the features that influence your model prediction. And then finally, Fairness Lens. This pattern talks about practices for ensuring that models treat different groups of users fairly, specifically for models that are trained on human-centered data. And a lot of folks use these terms, fairness and explainability, sometimes interchangeably. They are different, though they're pretty closely related. So I just wanted to highlight that on this slide. So fairness refers specifically to making sure your models are treating all users fairly. And explainability is understanding, the specifics of how and why your machine learning model is making predictions. So explainability can be one technique for uncovering fairness issues in models, but that's not the only thing you can do with explainability. So time to dive right into the patterns. The first one I'll talk about is Heuristic Benchmark. So to understand this, we'll start with an example. So we'll say that, let's say you're building a model using some public bike share data to predict the predicted duration of a specific bike rental. And you train a model and you find that the model's mean absolute error is 1,200 seconds. So that's great news, or actually is it great news? You don't really know, especially if you're trying to summarize this model to someone else, maybe to someone on the business team who asked you to build this model. If you just go to them and say, the mean absolute error is 1,200 seconds, they're not going to really have any context for that. So you don't know if that's good or bad, which is where the heuristic benchmark comes into play. So the heuristic benchmark is meant to provide a simple point of comparison when you're starting out building a new model. So some examples of good benchmarks could be, a constant number, maybe taking the mean, median, or mode from across your training data set, using a couple of parameters to slice that, or it could be human experts. So one example of this could be, let's say you're building a model to analyze medical imaging and predict the presence of something in a medical image. You probably want to compare first how your model is performing compared to, how doctors and medical practitioners would evaluate the same images. Oftentimes, folks will train a linear regression model on some data and use that as a baseline. And in some cases, that's good, but it's not necessarily the best heuristic benchmark because that isn't necessarily that simple to explain. So oftentimes, you want to pick something a little bit simpler than just training the model on training a linear regression model on your same data. So if we go back to our bike example, we could look at, as our benchmark, we could say, what is the average rental duration given this particular station and whether or not it's a peak commute hour. So we could run some data analysis on our training data and then see how our model performance is able to compare when using that simpler benchmark as an example. So just to wrap up, this pattern section is pretty short. I just put together a little flow chart to help you understand if you need this heuristic benchmark. So if you already have an operational model to do a similar or the same task, or an operational best practice in place, then that should be your benchmark. You don't necessarily need a heuristic benchmark. But if this is the first time you're training a model to do a specific task, then it's really useful to have a heuristic. So you can develop that heuristic, train your model. Let's say you're happy with that model and you decide to put it in production. You can now replace that initial model or that benchmark with the first version of your model and use that as your point of comparison moving forward. If you're not happy with the model you trained, stick with that benchmark or maybe try a different one and continue iterating on the model. So just a simple framework for understanding when you might need to employ this. So moving on to pattern number 2, explainable predictions. So explainability can mean a variety of things to different people depending on your role in an organization, various other things. In this case, I'm referring specifically to explainability of machine learning models, to understand how machine learning models are making predictions. So when we think about explainability, it's also important to think about who is using the models and how can explainability benefit different groups of people, because it's gonna benefit different types of people that are using your model quite differently. So for people like a lot of us, data scientists, ML engineers who are building models, we might use explainable predictions to understand why my model's not performing, maybe debugging strange behavior, and seeing how you can take that data and feed it back in to improve your model. The next group would be end users of ML systems. So this could be maybe you are using an app that gives you recommendations. In that case, you're the end user of this model that's generating those recommendations for you. The end user could also be, in the medical imaging use case, it could be a doctor that's looking at the results of, a model trained on X-ray data. And so they're using it to, enhance their trust in the model and understanding how they should respond to the prediction. And then finally, we have public stakeholders. So this could be either inside or outside your organization, folks involved in regulatory and compliance issues and standards related to machine learning models. These folks typically want a higher level summary to understand, how the model is performing and making sure that it complies with whatever regulations are in effect. And then further, this slide provides some examples of how these different types of users can take action from explanations. I won't go into all of these, but I'll share the slides out after. So what do explanations look like and what form do they take? This depends largely on the type of data that you're working with. So for image data, explanations can, and what I'm showing here is just one type of explanation. So this isn't all-encompassing, just one way you could use explanations on these different data types. So for image data, explanations could give you what's called pixel attributions to show you the pixels in the image that contributed to the model predicting a particular thing. In this case, this is a model that's predicting, this image is a husky, and the pixel attributions are showing us which regions caused the model to predict that. In the text example, we have a sentiment analysis model that's predicting, whether given text is positive or negative sentiment. And in this case, explainability can highlight the words that contributed to a particular prediction. And this example is actually showing how explainability can be used to uncover fairness issues. So in this case, it looks like our model is picking up on the right signal. So it's using the words not and love to understand the sentiment of this particular sentence. If it was instead using the word cake, that would not necessarily be the correct word to be honing in on, because the sentiment is really conveyed in the words not and love. It shouldn't matter what it's referring to. So if it said instead, how could you not love brownies, we should get the same sentiment score. So it's something you can use to make sure that your text model is picking up on the right signals. And then finally, for tabular data, numerical and categorical data, we get what's called attribution values for all the different features in our model. Attribution values can be positive or negative, indicating whether they push the model's prediction up or down. In this case, we're looking at a model that predicts the duration of a bike trip, and we're seeing the features that affected that most. So in this case, the distance of the trip caused the model's predicted trip duration to go down by about 2.5 minutes. So summary of this is that explanations look different depending on what type of data you're working with. And in the book, we talk about a few different solutions, some open source, and then one of the ones we talk about is how you can use Explainable AI, which is a service that we provide on Google Cloud. Today, there's a couple of different ways to use Explainable AI in Google Cloud. I'm going to show demos of 2 of these. So you can use it in AutoML tables, which is our solution for building models trained on tabular data, where you upload your data to a UI and you don't need to worry about writing any of the model code. You just press the train button, your model's trained, and then you can deploy it and get predictions through an API. I'm going to show a demo of that. And then we also provide Explainable AI in our AI platform product in a couple of different ways. So when you deploy a TensorFlow model to AI platform, you can deploy it with explainability enabled. And when you do that, you get feature attributions returned as part of your API response when you get predictions on that deployed model. And then our newest way that you can access Explainable AI is through our AI platform notebook offering. In this way, Explainable AI provides an SDK that comes pre-installed in these notebook instances. And this allows you to get explanations on a model that you have not deployed. So this is really useful if you want to get explanations as part of your model development workflow, which is a common way that explanations are used. And here you can get explanations on your model before you've deployed it. So you can use it to quickly iterate, see which features are important, use that data to improve your model perhaps, and then once you're ready to deploy a version of that to the cloud or wherever you'd like to deploy your model. So the examples that I showed in the previous slide by data type, those are all feature-based explanations. So there's many different types of explainability. It also depends on the type of model you're using. So the techniques on the right refer to models that are interpretable by design. And this refers to models where the architecture and the learned weights of the model can be used sometimes to get explanations and attribute predictions to features. So examples of this would be, simpler model architectures like decision trees or linear regression models. So in these types of models, the learned weights and other parameters themselves are informative and could be used for explanations. Post hoc explainers on the left refer to, more complex models, deep neural networks, where you can't use those models' learned weights to explain the predictions alone. So these techniques look at relationships between features and the model's prediction and use that to generate explanations. So the approach that we offer today is specifically feature attribution. So now I'm going to jump to a demo. And I'm just going to be conscious of the time. So Bill or Anna, just let me know if I should speed up since I know we're a little bit behind schedule. So what I'm going to show here is two demos, one of explanations in AutoML tables, and then using AI Platform Notebook. So to show you this AutoML tables demo, if you're not familiar with AutoML tables, this is what the UI looks like. And here I've trained a fraud detection model using a public data set that's available in both BigQuery and Kaggle. So the data set includes credit card transactions, and they've obscured the feature names in the data set. I made up new feature names just to make the demo a little bit more exciting. So these are fake feature names, but it's all real data from the original data set. So when you upload your data here, you specify the thing you want to predict. In this case, it's the class column, which indicates 0 or 1, whether the transaction is fraudulent or not. So once you've got a trained model, AutoML provides you with some metrics on how your model performed. And Explainable AI here is enabled by default. So we can see it here in the feature importance. So what this is telling us is for our test set, which features were most important to our model as a whole. So looking at all the predictions generated across the test set, and AutoML splits your data for you if you'd like. So it takes care of splitting your data into training and testing. So this is giving us an overall look at which features were most important to the model. So in this case, whether there was a smiley face in the signature. As I mentioned, these are just made up feature names, but it makes the demo a little bit more digestible. So this is global feature importance. AutoML tables also give instance level feature importance. So if I want to generate a prediction on my model, one way I can do that is in the UI. You obviously want to use the API to do this, if you've got a deployed model and users are generating a lot of predictions on it. But the UI is a good way to just test it out. So AutoML populates some random values for these features that I can use for testing. And if I check this generate feature importance box, when it generates a prediction, I can see feature importance values here. And let me sort that. So here, for this one particular example, we can see in this case which features were most important to the model. So that was AutoML tables. In the interest of time, I'm going to speed along to my AI platform demo. So for this, I'm going to show you an example in AI platform notebook. And I already have this notebook instance up here. Let me make the font a little bit bigger so you can all see it. So here I'm using the Explainable AI SDK, which I mentioned before. And I'm going to show you two image examples here. The first is a model that's just been trained on the ImageNet data set. And the cool thing here is that this model is just saved locally in my notebook instance. I haven't deployed it anywhere. But when I point the SDK at that directory, I'm able to generate some explanations on it. So as I mentioned, this is just a model trained on ImageNet. I am going to generate a prediction on this image of a jellyfish, and we'll see what explanations our model returns. And again, we're just pointing it at our local model. So we're using this load model from local path method, and it is looking at this ImageNet model directory and using that to generate an explanation. And let me just show this key so you can see what these colors mean. So here what we're looking at is it's giving us region-based explanations for this image to show which regions the model relied on most to make this prediction. And the most important regions are highlighted in yellow for this particular explanation method, and less important in darker purple. So in this case, we're just using explanations to verify that our model is able to understand the shapes that are specific to the different labels that our model's been trained to recognize. ImageNet has 1,000 different labels, so this particular model can recognize, 1,000 different things. In this case, it looks like it's a good sign because our model is using the shape of the jellyfish to make its prediction. If instead the background of our image had random swatches of yellow, it might be a sign that our model isn't using the right signals to make its predictions, and we want to go back to the training data and see how we can improve it. Maybe we don't have enough variety in the different labels our model's been trained on. So that's a simple ImageNet example. The next example is a medical example. I trained the model on a chest X-ray data set, also available in Kaggle. Some of you may have seen it before. So for this model, the focus here is not on accuracy. Obviously it's difficult to train a high accuracy model to do something like this, classifying diseases from chest X-rays. I just wanted to highlight how you could use explanations to improve this model. So I've trained a simple model on classifying, whether or not a certain condition is present in the chest X-rays, and using explanations here to highlight the regions that my model thinks are most important. One thing to note here is that the Explainable AI SDK returns this value called approximation error. And we tend to recommend that if it's over 5%, you should probably, not trust those explanations, or go back to your model and see, how you can improve it, how you can make sure that you can trust the explanations a little more. Because after all, explanations are only going to be as good as the quality of your model and the quality of the data you use to train it. They can't highlight anything, if you have a bad model, you can't necessarily rely on explanations to fix that. So this is a good, check to see, do you need to go back and change something about how you're generating the explanations, maybe change the explanation method you're using, or in this case, as I mentioned, model quality isn't great, so we probably need to go back and see, can we add more training images? Do we need to change our model architecture? So this approximation error can just be a good signal on if you need to go back and make some improvements to the model. So in this case, it looks like we do. And once we have a model we're happy with, the Explainable AI SDK has generated this metadata file, which we can see if we go into one of these directories, which we'll need when we deploy our model. So everything that we need to deploy the model is in this save model directory. And I'm not going to run this now, but all we need to do to deploy this model to AI platform is to copy this model directory to the cloud and then run this deploy command to deploy the model. So those are two quick demos of explainable predictions of that pattern. So with that, I'm going to go back to the slide, focus on one more pattern, fairness lens. And I know we're short on time, so I'll go through this pattern relatively quickly. So let's start with an example for fairness. So let's say that, imagine that you're in charge of, your organization is building a fashion classification model to identify different items of clothing and accessories from images. And you're in charge of collecting all of the shoe images in this example. So when you think of the shoe, just think about, now you don't have to shout it out, but what's the first thing that comes to mind? So let's say, as an example, that maybe you live in a climate that's warm all year round, and you wear sandals every day. All your friends wear sandals pretty much every day. So you go around collecting images of your shoes, of all your friends and family shoes, and you train this model. The accuracy is looking really good when you test it on your own images, but then the model gets deployed to production, and we have people with all different types of shoes, and they're uploading images, and it's not classifying them as a shoe. So this is one example of, one type of bias that can affect the quality of the model that you deploy. Obviously, there's many different types of shoes that we should account for when we're collecting images for this model. So I've highlighted in that example just one type of data bias. There's many different types of bias that can be found in data. The example that I mentioned that I showed with the shoes is what's called data distribution bias. In that example, we didn't correctly represent, we didn't have a good distribution of all the different possible types of shoes in the world in our image data set. You know, maybe it was 90% sandals and just a few images of other types of shoes. So that's data distribution bias. People often think that bias definitely means that there's a problem with the model. Data bias isn't necessarily bad. It often is harmful, but there are cases where bias is naturally occurring, and it's not necessarily bad. So one example is a fraud detection model that I showed before. In that data set, I think there's only like 400 examples of fraudulent transactions out of 250,000 data points total. And that's just the nature of anomaly detection. Something's an anomaly if there's not very many of them. So in that case, that's all the data you have available that's naturally occurring. It's not necessarily bad. You're just going to have to account for that in the way that you build your model. We also have a different pattern that talks about that, but I won't get into that today. So data distribution bias, we talked about with the shoe example. Data representation bias is, so let's say that you have one data point, that can have many different types of ways of being represented. In a shoe example, that was different types of shoes. So let's say we have a balanced representation of all these different types of things in our data. So for this, let's look at an example maybe of restaurant reviews. So let's say we've come up with all the different types of cuisine and food and restaurants that we'd like to represent in this data set, and we think that we have an roughly equal number of reviews for each of these different types of restaurants. So our data is distributed in a good way. But let's say that, for example, the seafood restaurants in our data set, 80% of the reviews are positive for them. But maybe our vegetarian restaurants, only 10% of the reviews are positive. So this is an example of bias in the way that the data is represented. So the data is balanced, but it's not necessarily balanced by the label in our data set. And this is going to have implications when we train a model and deploy it, because in the example I gave, vegetarian restaurants will have a much lower likelihood of reviews will have lower likelihood of being classified as positive. And finally, experimenter bias is the type of bias that can be introduced when you're labeling your data. Data labeling can take a long time, and so often people will outsource this task to a group of people to label the data. And labeling is often subjective, so there can be bias introduced in this phase. So let's take the sentiment analysis example again and say that we're having people label our data in terms of whether there's positive or negative sentiment in the data. So take the sentence like, I'm doing fine. So based on your culture, upbringing, where you are in the world, that sentence might be positive, or some people might interpret that negatively, like that's negative sentiment. So that's just an example of how different labelers might label something differently. And you need to account for that in your data labeling phase, just making sure you understand who's labeling the data and accounting for that type of bias. So bias can be introduced in your machine learning workflow at pretty much any phase throughout the machine learning workflow. The bias that I talked about on the previous slide were just in reference to data bias. So data bias that can be introduced in the data collection or labeling phase. But bias can also be introduced, for example, in the metrics that you choose, how you're going to calculate error as you're training your model. That can introduce bias as well. And then bias can also be introduced in the way that you decide to deploy your model and how users are interacting with it. So this slide is just meant to show that there isn't necessarily one place to go to look for bias. It can be introduced throughout the system, and it's important to just be aware of this and account for that as you're going through building and iterating on your ML model. In the book, we talk about a number of different techniques for solving for fairness. Here I'll just talk about one tool that we highlight called the What If tool. The What If tool is an open source tool that's developed by the PAIR team here at Google, stands for People in AI Research. It works on any model type, and it can be run from a variety of different notebook environments. So it's a widget that you can initialize in your Python notebooks. You can run it from Colab, TensorBoard, AI platform notebooks, probably a few environments I'm missing there. So the What If tool helps you understand how your model is performing, lets you inspect different data points in your model. And this is just a screenshot of, looking at the U.S. Census data set in the What If tool. As I mentioned, it's available in many different platforms. Lets you do a few different types of analysis, like counterfactual analysis, partial dependence plots. Lets you slice your data and understand how it's performing across different slices of the data. So this can help you identify, maybe your model is more accurate for a particular slice of your users, and it provides some techniques for how you can address that in your deployed model. It also lets you compare two different models. And it does integrate with our Explainable AI tool on Google Cloud. I'm not sure if I have time for this demo. Bill or Anna, feel free to chime in if I don't have time.
Yes, Sarah, we have a lot of questions actually.
Okay, yeah, no problem. I will switch to questions. So I'll just jump to this slide real quick to give one more shout out to pre-order the book if you're interested in what I covered, and definitely check out Lack's talk later today. He's going to be covering ML ops. I can send out the slides after, so other resources to check out are here. I'm gonna stop sharing and go check out the questions. But Anna, feel free to choose some that are that you think I should take. I'm just gonna.
Sure, I'll start with the easiest ones. Are the notebooks publicly available?
So some of the notebooks that I've shown are publicly available. I need to update the Explainable AI ones, but all of the code samples in our book is in a GitHub repo. I will share that in the chat. 1 second. Hold on. I'll share that. Yeah, we have a GitHub repo called ML.
Fantastic. That was another question, if the demos are in a GitHub repo. Will you share the slides?
Yeah, I'll share a PDF with you, and you can share that out with the group after the event.
Fantastic. I think that's good things to get out of the way. Next question. How can I use the design patterns to solve the bias in AI data? Jericho.
That's a great question. Probably a longer answer than I have time to give. But that's kind of what the responsible AI patterns are meant to provide is a framework for addressing bias. And there are different tools available for addressing bias throughout, each phase of what I highlighted. Some bias can be identified just from data analysis, like before you train a model. So one thing I forgot to mention is that the What If tool can be used without a model. So it can be used, if you just have a data set, you can initialize the What If tool, and it'll show you how balanced your data is across different features. So you can use that to identify data bias before you've even trained something. So that's one way of looking at it. I have a couple of blog posts on this. It's a long answer. Sorry, I can't give anything specific, but I think the summary would be just looking at all the different phases of your ML workflow or pipeline, and thinking about how bias could find its way into each phase, and then trying to address that. Someone pointed out a shoe museum that I'm going to have to check out in Toronto. I'll check that out. Other questions? I'm not in the Slack, so let me know if anything pops up there.
Another questions? I'll just say for everyone, because we have a lot of questions, we won't be able to go through all. Please post them in the Slack, and if Sara has time, she can answer later. For explainability.
Oh yeah, that's a good point. I'll pop in the Slack after I leave the Zoom, so I'll address the Slack questions later. But yeah, Anna, if we have more time, feel free to provide more questions.
Sure, let's go through a couple more. For explainability, do any of the tools platform provide an output of any unlabeled but numerically significant features?
Can you repeat that again?
For Daniel says, Daniel, please feel free to clarify for Sara. For explainability, do any of the tools platforms provide an output of any unlabeled but numerically significant features?
So a number of the tools we highlight, I don't know if I fully understand the question. I'll have to jump into the Slack to see it, but a lot of the tools that we introduce have different visualizations that they provide. So SHAP is one that I talk about. SHAP is an open source tool for explainability. You can check out their GitHub repo. They output a lot of different visualizations, both at a global and instance level, to help you understand how the model is performing. And the Explainable AI SDK also has some visualizations built in. I'll jump into Slack to give you a more detailed answer after. Good question, though.
Cool. How data bias can be reduced completely?
That's a great question. How can data bias be reduced completely? It can't always be reduced completely, like as in the case of the fraudulent data that I mentioned. Like in that case, less than 1% of the data might be fraudulent transactions, and that's where those are the data points that you care about the most. But you can do a lot of things to account for this. So like you can change some parameters when you're training a model to make sure that the model gives more weight to specific classes in your data. And after a model's been trained, it's really important to evaluate how your model's performing across different slices. So I'm just using fraud as an example here, but this could also apply to harmful bias. So let's say that we train a fraud detection model and the model accuracy is showing 95%. But when we look closer at how the model's doing on the fraudulent examples in the data set, maybe it's only able to identify 50% of them correctly, in which case it's actually not really performing well at all. So in that example, that's a case where the metric you choose to evaluate your model can also introduce bias. So if I had used accuracy to look at that model and say, okay, 95% accuracy looks good, I'm going to deploy it. But in reality, the fraudulent class was not performing well. So that's just a case where I should have used a different evaluation metric to look at the model. So that's one way that bias can find its way in. I'd say the best way, because chances are you're not going to be able to eliminate it completely. The best way, and I'm sorry if I already said this, is just finding ways to address it at different phases. So looking at your data, making sure that every possible group of user that might use your model is being represented fairly in the data, and then also looking at where there are areas that bias crept in during training that weren't captured in that phase is another way to look at it. But yeah, chances are you may not be able to completely reduce bias. It's just a matter of having a framework for addressing it.
Thank you, Sara. And last questions. For the rest, we'll have to move to Slack. What is the bigger challenge for AI explainability nowadays?
Great question. What is a big challenge for AI explainability? So yeah, that's a great question. I think giving people techniques to improve their trust in the explanations that are provided for a model is kind of like something that's important now. So what I mean by that is when you look at, let's say you don't have explanations for your model and you're just looking at accuracy. That's kind of going like, or whatever metric you choose, that's kind of going one level deep. Then when you look at explanations, that gives you additional insight into how your model is performing. But you also shouldn't take the explanations at face value. You need to be able to understand, how much you should trust those explanations And I talked about that a little bit with the approximation error that I referenced, but just giving people, I think, the right tools to be able to understand and know how to take action from their explanations. I think that'll be really important moving forward. It's a relatively new and emerging area in machine learning. There's constantly, different explanation methods that are being developed. So I think that's another area that we might see new developments is research around generating explanations for different types of models. I didn't have time to talk about that, but our offering on Google Cloud, we provide 3 different explanation methods called integrated gradients, Shapley, sampled Shapley, and X-ray. And these are all based on publicly available research, but I'm sure we're going to see that space evolve, more research to handle, how to provide explanations for all different types of models. That's a really good question. And I will go to the Slack in a few minutes to take a look at the rest of the questions. These are great. Feel free to connect with me on Twitter as well, @SarahTweets. Send me a tweet or a message if there's anything you have questions about that I didn't cover here.
Fantastic. Thank you so much for your time, Sarah. This is such a new hot topic, very helpful. We appreciate you. And you can see Sarah at the AIDevFest Northeast on Halloween. So watch out for that if you want to hear more.
Awesome. Thank you, Anna, and Bill, and everyone that helped put this event together. And I hope everybody enjoys the rest of the session.
Thank you, Sarah. Enjoy your day and see you again next month.